All right, so welcome back. We're now in the 4th week of the semester, and today we'll be starting a new chapter, and that will be on vectors. Just by a show of hands, does anyone here have any prior experience dealing with vectors? Okay, and if that's the case, was it in a physics class or some other class where you saw vectors? There's physics? Yeah, that's what I figured. So we're going kind of out of sequence with the chapters. We did chapter 3, and we finished it last week. Now we're going to move back to chapter 2. So in our textbook, chapter 2 is purely a math chapter, which deals with the mathematics of vectors. So that's what we'll talk about this week. So let's start with a definition. We want to understand what a vector quantity is, and the best way to do that is to contrast it with another type of quantity, which we call a scalar. So let's start with that, actually. A scalar quantity is anything that is completely described just by a number alone. So in other words, if you get the full information about the quantity just with a single number, what you have is a scalar. And importantly, there's no direction associated with a scalar quantity. It doesn't even make sense to refer to a direction. So let me just give you a couple examples, right? The number of people in the room. If I said there are 20 people in the room, that would make sense. If I said there were 20 people in the room east, that just doesn't mean anything, right? There's no direction associated with that type of quantity. A vector quantity, on the other hand, has a direction associated with it. It makes sense to refer to a direction. And in fact, if we're dealing with a vector quantity, we need to know the direction to fully specify what it is. So an example that I can give you for a vector quantity that we're going to encounter a lot in physics is force. So force is basically when you push or pull on something. And when you do that, it matters the direction you exert that push or pull. So it's different, for example, if I push the table this way versus pulling it in this way. Those are different forces because the direction actually matters there. Okay? So I thought real quick we could just do an example or actually come up as a class with some examples of scalars and vectors. So we all understand the difference between the two. So let's try to think of 3 examples of a scalar quantity. Anyone can try to shout one out. So something that just doesn't have a direction associated with it. There are lots of examples of this.
20 apples.
Yeah, so any kind of counting, counting the number of things, so counting a number of apples, number of people in the room. Can you think of anything else?
Kind of volume.
A volume, yeah. If I were to take some kind of space and measure its volume, that would be a scalar. You said time. Yeah, time would be another good example. What about some vector quantities? Does someone have a question? Okay. What about some vector quantities? Can you think of some examples of those? We already said force. Can you think of any others?
Velocity?
Yeah, velocity is a good example of a vector quantity because velocity has a direction. It's a different scenario if we're moving in the positive x direction or the negative x direction for 1D motion. And we'll see once we're in 2D motion, there's more options for the direction of velocity. Okay? Any others?
Displacement?
Yeah, displacement has a direction. You can be displaced in one direction or another. I'll give you another, acceleration. That has a direction too. Okay, so a lot of different quantities in physics are vectors, is the point here. Okay, so one thing that we're going to do quite a bit when we're dealing with vector quantities is we're going to make graphs or diagrams of those vector quantities. And this is how it's generally done. How do we represent a vector on a diagram? Well, a vector has 2 parts, okay? One of those parts is the magnitude. So when we talk about the magnitude of a vector quantity, we're just talking about its overall size without referencing its direction. So the size of the vector quantity, that's the magnitude. On a diagram, we show the magnitude by giving an arrow a certain length. So an arrow that has a very big length has a large magnitude. An arrow that has a smaller length has a smaller magnitude. That would be the idea. Now the magnitude, by the way, might have some units attached to it depending on the situation. So an example of that would be if we had a velocity vector, the units might be meters per second or miles per hour. The magnitude of the vector would have those units associated with it. Okay, what about the direction? Well, that's pretty straightforward because the arrow in our diagram is pointing somewhere. Whichever way it's pointing, that's the direction. And typically, we give the direction by specifying an angle, okay? So if I have some kind of reference line, which I'll show you with this dashed line here, the direction of my vector would just be the angle that my vector makes with respect to that line. So again, magnitude is just how long the arrow is, and then direction is which way it's pointing, and we can specify that by giving an angle. Does that make sense? Okay. So what does it mean to say that two vectors are equal to each other? That's what I want to get into here. When it comes to vectors, we totally describe them just in terms of magnitude and direction. There's no other information we need. So if two vectors have the same magnitude and they're pointing in the same direction, we say they're equal mathematically. And it doesn't matter where the starting point of the vector is on our diagram. So if you look at all of these vectors here, they all have the same magnitude. They're all pointing in the same direction because they're all facing the same way and they have the same length. The only difference between these is some of them start at different points, right? Well, that doesn't matter as far as the equality of the vectors is concerned. Because they all have the same magnitude and direction, they're all equal to each other, okay? So the starting point doesn't matter. All that matters is your magnitude and your direction. Does that make sense? So I'm going to give you a little exercise to do based on this idea, okay? So we have three vectors here. We have vector A, which points from 0, 0 to 1, 1 in the xy plane. Okay, so it starts at the point 0, 0, and then it ends at the point 1, 1. Vector B goes from the point 2, 3 to 3, 4 in the xy plane. And then vector C goes from the point 3, 3 to 2, 2. Okay? So these three different vectors, I want you to determine which one of these statements is correct. So is it just that A is equal to B, but not equal to C? Is it that A is equal to C, but not equal to B? Is it that B is equal to C, but not equal to A? Or are they all equal to each other? That's what you want to determine. So the way I would go about doing this is at your desk, just draw the picture of all three of these vectors, and just looking at that picture, you should be able to answer the question. Okay? So take a minute to draw the picture of these three vectors in the xy plane and see what you come up with for your answer. And if you have graph paper, that'll be useful for drawing these pictures too. What's the answer then? Okay, so let's see what those diagrams look like now that you've had a minute to try to work it out at your desk, okay? So what we're going to do here is construct the XY coordinate system. And on the x-axis, I'm just going to mark off the points 1, 2, 3, 4. And then same on the y-axis. That's all we'll need for this part. Okay, so let's start by drawing vector A. Vector A starts at 0, 0, that's the origin. And then it ends at the point 1, 1, which is right here. So we'll show an arrow just going from the starting point to the end point. And that is vector A. By the way, when I indicate a vector, I put a little arrow over the quantity. That's just a notation thing, okay? Vector B, that one started at the point 2, 3. So here, 2, 3 is right about there in my coordinate system. And then it ends at the point 3, 4. So the point 3, 4, that means x is equal to 3, y is equal to 4, is like this. Okay, so my vector, vector B should be shown like this, okay? So right away, what can I say about A and B? Are those equal? They have the same length. The length is actually root 2, if you work it out, and they're pointing in the same direction. So it's certainly true that A is equal to B. But is it true that these are also equal to C? Well, vector C goes from the point 3, 3, which is actually over here, and then it ends at the point 2, 2. So the thing about vector C is it points the opposite way to these other vectors, so it's not equal to them. Okay? It doesn't have the same direction. Make sense? Okay, so vectors are specified by a magnitude and a direction. That's what we need to know so far. So now that we've established the very basics, let's now get into different ways of representing vectors in terms of numbers. Okay, and we'll show two approaches to this. We'll have something called polar form and Cartesian form. Okay, and we'll explain what each one of these are and actually how you can sort of translate from one form to the other. That's an important part of this. Okay, so what are these two different ways to represent a vector? Let's start with polar form. When we give a vector in polar form, we're giving the magnitude of the vector, so we're given its length, and we're given its direction. That's basically it. We have those two pieces of information. Okay, Cartesian form is something slightly different. We describe the vector in this case in terms of x and y components. If you don't know what I mean by x and y components yet, don't worry, we're going to define that later. But that's just what it is for now. So the thing is, we can use either one of these forms. Either one is just as valid as the other. They both completely describe the vector and what the vector is doing. And you can always go from one to the other. So in other words, if I have my vector in Cartesian form, there's a way to translate that into polar form and vice versa. But one thing that we'll see as we move on, probably won't get to this until Thursday, but when we add or subtract vectors, typically the best way to do that is to work in this Cartesian form. So when it comes to adding and subtracting vectors, usually what we do is we break things down into their x and y components. Okay? So that's kind of a big picture summary of where we're going. We're going to fill out the details of all this as we go. But any questions so far? Okay, so let's start with polar form. Now, we've already kind of explained what this is, right? We need a magnitude and a direction to describe a vector in polar form. So as we go through this lecture, what I'm going to do is refer to just some generic vector in the xy plane, and I'm going to call it A. So vector A is just the one we'll work with as we go forward. And A, with a little arrow on top of it, is just to denote that we're dealing with a vector. Okay, that's just a little bit of notation. Another way to notate that we have a vector is to put it in boldface. So you see how at the very top I say vector A in boldface? You can do either one, okay? But typically if you're just writing stuff by hand, you put the arrow on top because it's hard to write in boldface, right? Okay, so we need two numbers here. The magnitude is the length of the vector, as we said. And the way we show this mathematically is to put the absolute value symbols around the vector A. So if you see any vector with the absolute value sign around it, that means we're taking the magnitude. That means we're just considering the length of that vector, okay? And one thing that's really important to know about the magnitude of a vector is it's never a negative number. Because it's a length, it's always something positive, or could be 0, but it can't be negative. That just doesn't make any sense. As far as the direction, remember, we are typically going to give the direction of a vector using an angle. And so you have to ask, what are we measuring our angle with respect to? So let me just show you there are different ways you could potentially do this. I could measure the angle of my vector off the y-axis, right? I could measure it off the negative x-axis, so starting here and then looping around to there. There are different ways you can measure the angle. So just so we're on the same page about how we're measuring the angle, we take the measurement of the angle off the positive x-axis going counterclockwise. Okay, so we start here on the positive x-axis, we go counterclockwise, and that's how the angle is defined. Okay, there are other ways you could do it, but this is the convention we're going to use. Okay, makes sense? So we start here, go counterclockwise, that's our angle. Make sense? Okay, so because we're dealing with angles, what we should do is just a little bit of review about angular quantities and the different units we can use to measure an angle. So we have basically three units for angular quantities that you're going to see in this class and in Physics 45, 46, and 47 going forward. We have degrees, we have revolutions, and we have radians. Okay? So everyone's probably familiar with degrees. We know there are 360 degrees in a full circle. Radians, we know there are 2 pi radians in a full circle, but you may need some reminding about where this unit of radians actually comes from, so we'll get into that. And then revolutions, that's pretty straightforward. Just how many full times do we go around the circle? Okay? So if we want to jump from one unit to another, this will give us our conversion factor. 1 revolution, so 1 full lap around the circle, is the same as 2 pi radians, is the same as 360 degrees. So this will allow us to convert any kind of angular quantity in any way we want. So actually, let's get into radians real quick. You guys remember how radians work from math? Maybe a little shaky on that. Okay, this is how a radian is defined. Or more accurately, this is how we take an angle in radians and define that measurement. So what you do is you imagine a circle, and the radius of that circle is r, okay? And then we cut a little slice out of that circle. And of course, that will take up some angle theta within the circle, okay? Now notice that across from the angle theta, we have what's called an arc length. So it's not like the full circumference of the circle, it's just a little piece of the overall circumference of the circle, and we call that arc length s, okay? So this is how we define the angle measured in radians. We take the arc length on the circle across from that angle, which is s, and then we divide by the radius. So if you take an arc length and you divide by a radius, you get theta, the angle in radians, okay? Does that make sense? You guys seen this before? So let's actually think about how this works out conventionally speaking, okay? An arc length, well, that's a length, might measure it in meters. The radius, that's another length. You can also measure it in meters. So what happens if I take a length divided by another length? What kind of quantity am I left with? That's called a dimensionless quantity. It's just a pure number, right? So if I take like 2 meters divided by 1 meter, I just get the number 2. It doesn't have any units attached to it, okay? So technically speaking, this way of defining an angle gives us a dimensionless quantity with no units. But we just tack on radians to remember that we're not talking about degrees and we're not talking about revolutions, just so we don't get the units screwed up, okay? We all good on that? Okay. So I have a question for you. Remember the way we define the angle of a vector. You go off the positive x-axis and you go counterclockwise, okay? So let's say we have a vector that lies directly on the negative y-axis. It's just pointing down towards the negative y-axis. What would the angle for that vector be? What would our standard way of specifying the direction be? If you can't immediately see it, just draw the picture and see what angle your vector is making with the x-axis. Okay. just take about 20, 30 seconds to draw that picture, and then we'll choose the answer. All right, what do we think? So someone said 90, and then other people are saying D, 270. It's actually going to be 270. Okay, let's see why. So the answer is D, 270. So again, just draw the vector in the xy plane. Let's draw our x and y axes like this. And what we're saying is this particular vector points just straight down the negative y-axis. So let's call this vector A, as we typically do for a generic vector. Remember the way we measure the angle. We start on the positive x-axis, and then we go counterclockwise like this, okay? So clearly, we're going to have 90 degrees, plus 90 degrees, plus another 90 degrees to get to this point. So this angle, which we typically call theta, by the way, theta, is equal to 270. Make sense? What if I had a vector that was on the negative x-axis? What would theta be?
180.
In that case, you'd have 180, right? Okay, so looks like you get it. So then, we need to talk about something called unit vectors, okay? So what is a unit vector? Okay, let's say we have an x, y, and a z axis that we've already established. So we've already set up some kind of coordinate system, okay? Unit vectors are just vectors that point along each one of those coordinate axes that we've set up. And they're called unit vectors because they have unit length. In other words, they have a length equal to 1, okay? So if you have a set of vectors, each one has a magnitude or a length equal to 1, and they point along all the axes, those are your unit vectors, okay? And we typically give these names when we're dealing with x, y, z coordinates, okay? So here's my x-axis, here's my y-axis, here's my z-axis in this picture. The vector I hat, we literally call this I hat, it's a lowercase I with a little hat on top of it, is pointing along the x-axis, has a length of 1. Okay, the vector j hat is pointing along the y-axis, and it has a length of 1. And then k hat points along the z direction, also has a length of 1. Okay, so I, j, k goes with x, y, z. So for now, I'm just telling you we can describe these vectors, right? But later on, what we'll see is these unit vectors are kind of like the building blocks of all other vectors. In other words, if we combine these unit vectors in the right way, we can get out any vector you want. That's what I mean by they're the building blocks of all other vectors. Okay, but for now, that's just a definition of the unit vectors. Okay, so any questions so far? So now we've got our unit vectors. With those unit vectors, we can now talk about the other way of representing a vector. So we did polar form. Remember, that's magnitude plus direction. Now we have something called Cartesian form, which is defined in terms of x and y components. So let's first give like the general format for writing a vector in Cartesian form, and then let's explain what this actually means. Okay, so what we say is vector A, written in Cartesian form, is a sub x times I hat, that's our unit vector in the x direction, plus a sub y times j hat. That's the general way we can write a vector in Cartesian form. And of course, if we had a z-axis, we'd have a third term for that component as well. But for now, let's just stick to x and y components, okay? So let's draw the generic vector we have. Okay, let's say it's pointing off into the first quadrant this way. What I'm going to do to pick out the components of the vector is I'm going to project this down onto my x-axis. So you see what I'm doing? I'm taking the tip of the vector and then just projecting it down onto the x-axis, okay? Now the length that that projection takes up on the x-axis, that's just what we call the x component, right? And in a similar way, if we see how this vector projects onto the y-axis, that's the y component. So that's how we define ax and ay. And these numbers can really take on any value you want. They can be negative even. Because you can have a vector that's pointing along the negative x direction or along the negative y direction. So the magnitude, we said, can't be negative because it's just the length of the vector. But these components can be negative, okay? Now, I want you to notice something that's happening in this picture that's super important for basically everything involving vectors going forward. When we show the vector itself and its components, we construct a right triangle. Okay, you see we have a right triangle here. That right triangle and the geometry associated with it is going to tell us how to analyze the vector. Okay, we'll get into that in a second. But what I'd like to do first is go into a little more detail about what I mean by the components. Okay, so this right here is just sort of a useful mental picture for visualizing the components of a vector. Okay, you may already kind of get it from the last picture, but if not, maybe this will help. So remember, we said the components of a vector are just projections onto each axis. So how can we just visualize this in a more clear way? So let's say, just for this example, we have vector A shown here, and we want to pick out its x component. Here's one way we could do that. Imagine a source of light, like the sun, which is directly shining down onto the x-axis, right? And imagine that this vector is casting a shadow, and it's basically blocking these rays of light that are coming down, right? So what it will be doing is casting a shadow onto the x-axis. Okay, the length of that shadow is basically our x component. Okay, so the larger our x component, the longer this shadow will be. Okay? By the way, if there's no x component, meaning the vector is just along the y-axis, you imagine doing this and there's no shadow cast at all, right? So there would be no x component. You can imagine doing the same exact thing on the y-axis too, right? Just shine your source of light from this direction onto the y-axis and see what kind of shadow is cast here. It's the same idea. So that's just a picture you can have in your head for what the components mean. Okay? Any questions on this? Pretty straightforward so far, hopefully. Okay, so we are moving kind of fast, but we'll keep going if there are no questions. Okay, so what have we done so far? We've said you can write a vector in Cartesian form. That means you have x and y components. And you can also write a vector in polar form. That means you have a magnitude and a direction. So how do we go from one form to the other? That's what we want to establish now. Okay, so the way we get the relationships is based on that right triangle I showed you earlier. So I'm just going to copy it down here. Remember, we had the vector pointing like this, and then we picked out its x component, which is the projection of that vector on the x-axis, and its y component, which is the projection along the y-axis. Okay? So basically, we have the overall length of the vector, or the magnitude, being the hypotenuse of this right triangle. Okay? And then the components being the other two sides. And then we also have our angle theta, which gives us the direction of the vector right here. Okay? So what we're going to do, just as an exercise, is remember our sines and cosines and use that to solve for the x and y components. Okay? So we'll come back to this, but let's work out the relationships on paper, and we'll do that now. Okay. So here's our picture. We have the magnitude of the vector as the hypotenuse of this triangle. And then we have ax down here. And then we have ay up here. This is a right angle. between x and y, that's always going to be a right angle. And then this is our angle theta, which tells us the direction of the vector. So here's what I want you to do. Just remind me of what the definition of cosine of an angle is.
Adjacent over hypotenuse.
Yeah, cosine is adjacent over hypotenuse. Okay, so in this picture, what is our adjacent side? It's AX, right? So it's the side that's adjacent to the angle, but not the hypotenuse, so that's AX. Okay? And our hypotenuse, we already said, is the magnitude of A, right? So solve for AX. What do you get? AX is equal to the magnitude of A times cosine of theta. So you see, if we have the magnitude and we have the direction, we'll use this to solve for AX, to get the X component out. Okay? Now, also remind me, what is sine of theta? What's the definition?
Also theta over hypotenuse.
It's the opposite side divided by the hypotenuse. And what's the opposite side in this case?
A1.
That would be AY. So sine of theta is equal to AY divided by magnitude A. Okay? Which tells us AY equals magnitude A times sine theta. So that's where the relationships that we saw on the slide earlier actually come from. Now, one really important thing to note. This only works if we're using this angle theta right here. In other words, if we're using the angle off the x-axis. If we're not using this angle, this all breaks down. So if you're going to use these formulas, make sure that you have the angle off the x-axis and not something else. Okay? So to summarize, we have AX equals magnitude A cosine theta. We have AY equals magnitude A times sine theta. And these relationships are only valid if we're taking theta to be off the x-axis going counterclockwise like this. As long as that's the case, these will work just fine. Okay?
Does it work with other reference angles or just off the in quadrant 1?
Yeah, so you don't have to be in the first quadrant. You could be in any quadrant and this would still work. But as long as we're taking this off the x-axis. Yeah. So we'll get into the different quadrants later. So we have a more general idea. Okay, so here's a vector. Vector A is shown on this figure to the right. It has a magnitude of 6 with no units. It's just a dimensionless magnitude. And it's oriented at 120 degrees from the x-axis. So express this in Cartesian form. Just a quick plug and chug based on the formulas we derived. So try it out, take a minute, see what you get. All right. You can actually determine the right answer without calculating anything. based on the options here. Can anyone just see what it is?
B.
Okay, how do we know?
Negative, like, the x is pointing the negative direction.
Yeah, so you see how with answer choice B, we have a negative x component, and then we have a positive y component. The vector you see here is in what we call the second quadrant. So it has a positive y component because it projects up here onto the positive y-axis, but it projects down here onto the negative x-axis. So it has to have a negative x component, positive y component. And there's only one answer choice that actually fits that description, right? But let's just do the calculation real quick. Okay, we've got ax equals magnitude A times cosine of our angle theta. So what we do is we take 6 cosine 120 degrees. And what does your calculator return for this?
Negative 3.
Returns negative 3. We keep 2 sig figs on that. And then ay, that would be the magnitude A times sine of theta. So we just take 6.0 sine of 120 degrees. Make sure you're in degrees mode, by the way, on your calculator. And then what does the calculator return for this result?
5.2.
Returns positive 5.2. So what does that give us? A, if we write it out as a full vector, is minus 3.0 I hat plus 5.2 j hat. That's the standard format. Okay? All right, so hopefully that's pretty straightforward so far. So to keep it moving, you can probably guess what the next thing we're going to talk about is. If we know how to go from polar form to Cartesian form, we should also know how to go the other way, right? So if I already have the x and y components, can I find the magnitude and the direction? Well, of course, and the way we're going to figure it out is to use the same right triangle that we used before to work out the other relationships, okay? So I'm going to go back to this slide, but right now I just want to work out those relationships and then we'll summarize, okay? So I'll copy down the right triangle that we've been working with, where we have magnitude A as the hypotenuse, and we have AX and AY as the other two sides of the right triangle, and then we take theta to be this angle with respect to the x-axis, okay? Okay, so the Pythagorean Theorem, let's start with that. What's the basic statement of the Pythagorean Theorem?
C squared is equal to A squared plus B squared.
Yep. And C is always the hypotenuse in this equation, right? So C squared equals A squared plus B squared. In this case, our hypotenuse is the magnitude. We'll have the magnitude on this side of the equation. And if we want to get the magnitude itself and not the square of the magnitude, we'll square root on both sides. And of course, my A and B sides are AX and AY. So I'll have AX squared here, AY squared here. So it's just the hypotenuse of this right triangle. We use the Pythagorean theorem for that. Okay? Now, to build up these other relationships, we used cosine and sine. And we haven't used tangent yet. That's an important trig function. Let's just write it down and see if it tells us anything. Tangent theta equals, okay, what is the definition of tangent without plugging anything specific in? It's, opposite divided by adjacent, right? Okay, and in this picture, what is my opposite side?
A1.
That's AY, it's across from the angle theta. My adjacent side, AX. So here, let's just write it down. Tangent theta equals AY over AX. So if I wanted to know theta, what would I do as a next step to solve for theta?
Inverse tangent.
Yeah, so I would take the inverse tangent of y over x, but there's actually some subtlety to that we have to get into, okay? So when you take the inverse tangent, don't just blindly trust what your calculator is telling you. There's a little bit of subtlety to this, so we'll get into that next, okay? All right, so this takes us to the idea of the different quadrants in the xy plane. Okay, so for the most part in this class, we're simply going to be dealing with two-dimensional vectors that lie in the xy plane. And so we can break up that xy plane into the four different quadrants. We're all familiar with this idea of the four quadrants. Okay, let's just review real quick. First quadrant is up here, and then we go counterclockwise to get to the next one, and then the third and the fourth are here. Okay? So what really characterizes the first quadrant? Well, if you're in the first quadrant with your vector, something pointing like this, both your x component and your y component will be positive. So if we're in the first quadrant, ax and ay are both positive. But another way to think of it is in terms of the angle. Okay? If theta is equal to 0, that means our vector is lying right on top of the x-axis like this. If it's equal to 90, we're right on top of the y-axis like this. So in the first quadrant, we're somewhere in between 0 and 90 degrees, right? Okay, if we're in the second quadrant, now we have negative x values, but positive y values. And then if we think of this in terms of our angle, we're anywhere between 90 and 180. Okay? Third quadrant, now both x and y are negative. And if we think about this in terms of an angle, we're anywhere between 180 and 270 down here. Correct? Okay, and then finally in the fourth quadrant, x is back to being positive, but y is still negative. And what is our range of angles? We have 270 all the way to 360, okay? So the way we define the angle, it can be anywhere between 0 and 360, and that covers all of the quadrants. Does that make sense? But that gives us a problem when it comes to the arctangent, or the inverse tangent function, okay? So if you have your calculator, just take it out for this next part, okay? So arctangent function is written a lot of different ways, unfortunately, depending on what textbook or source you're reading. You might see this written as tangent inverse, like this. That's typically how I'm going to write it, but sometimes it'll also be written arctan, like this, or sometimes just atan, like this. These all mean the same thing. It just means we want to undo the tangent function to solve for what's inside, okay? And what I want to get across here is you need to be careful if you're ever using the inverse or arctangent function. So here's an example to get the point across, okay? So let's say that I have this vector A, which is minus 3 I hat and then minus 2 j hat. And clearly that's in the third quadrant because both the x and the y component are negative, correct? And what does that mean about the angle? What range of angles should we be looking at for this vector?
180 to 30.
Yeah, so because we're in the third quadrant, just like we said before, the angle is somewhere in between 180 and 270, okay? But let's see if we plug these numbers into the calculator, if the calculator actually gives us something in that range, okay? So remember, tangent theta is ay divided by ax, right? So if we took the inverse tangent of ay divided by ax, that should allow us to solve for theta, right? We can say theta equals inverse tangent ay divided by ax, okay? So let's just plug the numbers in. Ay is minus 2, because it's associated with j hat, that's how we know. And then ax is minus 3, associated with I hat, that's how we know. So inverse tangent minus 2 over minus 3. Well, the negative signs actually cancel, right? So that's the same exact thing as inverse tangent 2 over 3. And maybe you can already see what the problem is. Because this would be like calculating the vector angle in the first quadrant, right? Because we've canceled out the negative signs. So punch this into your calculator, do inverse tangent 2 over 3, and then see what you get. Yeah, so you agree? Did you try it out? Did you get 33.7 degrees? That's wrong, right? It's not the right answer. So this is what I'm getting at. You don't just blindly take the result of arctangent and move on. You do have to think about which quadrant you're in and then correct your answer, okay? So we're convinced that that's the case, hopefully? Okay, good. So rather than giving you like an example of every possible thing that can go wrong here, I'm just going to tell you a set of rules to follow to correct your angle depending on what quadrant you're in, okay? So here's what you do. It's all laid out in this table, okay? And we'll go over this in a second. But the basic problem is the arctangent function, it only ranges between minus 90 degrees and 90 degrees. That's the range of values it can output. But our angle is supposed to go between 0 and 360, right? So there's a mismatch there. The range of our angles to specify the direction of a vector doesn't really match what arctangent spits out, okay? So there's a simple correction we can make, and it's all spelled out in this table, okay? So if your vector is in quadrant 1, if you're in the first quadrant, we know that our angle is supposed to be between 0 and 90. And actually, that's exactly what arctangent will spit out if you do this calculation I showed you earlier. So what do? You just take that as your answer and you don't need to correct it. It's already correct, okay? If you're in the second quadrant, if you just plug in ay and ax to the arctangent function, it's going to spit out something between minus 90 and 0. So here's how you correct for that. What you do is you simply add 180. So if you're in the second quadrant, do arctangent of y over x, and then add 180, and that will be the correct angle, measured off the x-axis, okay? It's actually the same correction if you're in the third quadrant, you just add 180. But if you think about what arctangent spits out, it ends up between 0 and 90. But the correction you do is you add 180, okay? And then finally, if you're in the fourth quadrant, once again, arctangent is going to give you something between minus 90 and 0, if you plug it in. And the way to correct that one is to add 360, okay? So that way, our angles will be between 0 and 360 if we apply this correction. Does that make sense? All right, so just keep track of which quadrant you're in. Remember, if you're in quadrant 1, don't change anything. If you're in 2 or 3, you add 180. And if you're in 4, you add 360. That's all you need to know. Okay. So with that in mind, let's say we have this vector. We have the vector minus 4i hat and then minus 3j hat. What I want you to do is express this same vector in polar form. So that is, find the magnitude and find the direction. And when you find the direction, just round your answer to the nearest degree. Okay? So the way I'm presenting it here is just the first number is the magnitude, second one is the direction. So which one of these is right? Take a minute to work it out. Okay, it looks like some of you have got this already. If not, that's cool. We just want to chug ahead on this lecture. So let's go through it together. So here's what we have. We're going here from Cartesian, that is XY form, into polar form. That is, you have the magnitude and you have the direction, okay? So let's just grab the relationships that we derived earlier. The magnitude of A is the square root of ax squared plus ay squared. And in this case, what goes in for ax?
3.
So here, let's remember the vector was A equals minus 4 I hat minus 3 j hat. So this is ax, the one that goes with our I hat unit vector, and this is ay. That's how this works. So what we have is the square root of minus 4 squared plus minus 3 squared. This actually works out to exactly 5. So 3, 4, 5 is a Pythagorean triple, if you remember. Okay, now I want to get the angle. Before I do that, let's establish which quadrant we're in. Which quadrant are we in with this vector?
3.
We're in quadrant 3. Just write Q3 because both ax and ay have negative values. Okay? So therefore, if we want to know what the angle theta is, we'll take the inverse tangent of ay divided by ax. And then what's the correction we make to this? Add 180. So we'll take inverse tangent of ay, which is minus 3, divided by ax, which is minus 4. So those signs actually cancel on the inside. And then add 180 to that. So if you work this out, you'll find it comes out to 217, just rounding to the nearest degree, as we were told. Okay? By the way, if you wanted to check that you did this right, let's actually do this. We already know what ax and ay are supposed to be. So if we plug those back into, so this is just like a check the answer type thing. But ax is supposed to be magnitude A times cosine of my angle, right? So if I take 5 times cosine of 217 degrees, try it out. And at the same time, if I remember the formula for ay, it's the magnitude A times sine of my angle. So if I punched into the calculator 5 times sine of 217, what should I get back? I should get back the x and y components that we started with. Okay? So you can try this out and see that it works, but ax will return minus 4, ay will return minus 3. Okay? So, any questions on this? All right. So let's keep it moving. We're going to spend the rest of the time today, and pretty much the rest of the time on Thursday, talking about adding vectors, how this works, what are the different ways of adding vectors, and when is this relevant in physics in particular. So now that we know how to represent vectors in both Cartesian and polar form, and we know how to switch between them, we're ready to talk about this, adding vectors. Okay, so right away, I just want to put out a word of caution, okay? Adding vectors is more complicated than adding scalars. Adding scalars is pretty straightforward, right? We're just adding numbers together. That's not what we're doing when we're adding vectors. And the reason is the direction of the vector matters, okay? So if I have a vector with a magnitude of 3 and another vector with a magnitude of 2, I don't just add them together and get a magnitude of 5, for example. It depends on which way the vectors are pointing, okay? So there's more to it. So what we're going to do is outline two basic methods for adding vectors. And the first one we'll cover today, the second one more on Thursday. Okay? So the first method we'll learn about is a graphical method. So what we do when we take the graphical approach to adding vectors is we draw all the vectors that we are adding together onto a diagram, and we have to make this drawing pretty carefully. We have to make sure the lengths of each vector and the angles associated with each vector are measured as precisely as we can. And then we actually find the answer. We find what the sum of those vectors is by just making a measurement straight off the diagram. Okay, so if we draw it accurately enough, we can get a pretty accurate answer just by making a measurement off the diagram. That's one way to do it. And it's not really that practical, because on a test, you want to punch numbers into a calculator. You don't want to sit there and make the nicest drawing in the world, right? But we want to know how to do this to start off. Then we'll learn about algebraic methods. So with algebraic methods, we're not making a drawing necessarily. We don't need that. We're purely expressing the vectors involved in terms of numbers. And what this typically boils down to is breaking each vector up into x and y components, and then adding the x components together, and then adding the y components together. So I'll show you how that works when we get to it. But as I mentioned earlier, this is usually going to be more convenient to make a quick calculation rather than having to make a super precise diagram. Okay? So these are the two methods we're going to start to explore starting now. Any questions? Okay. So let's get into how we draw a vector diagram. And on this picture, on the slide here, I have an example of a vector diagram, but there are really a whole lot of different examples we could have picked out. So what's the general process here? We start by drawing the x and the y axes. So draw your axes. Typical thing to do is have x going to the right, y going up, right? Okay, next thing we do, we don't just immediately draw the vector. What we do next is we choose something called a scale factor. Is anyone out there familiar with this idea of a scale factor? So let me show you an example of when a scale factor is used in everyday life. If you're ever reading a map, you may see a little indicator at the bottom of the map with a bar that says this length represents, I don't know, 10 miles, 100 miles, whatever. That's an example of a scale factor, right? In other words, we want to know what physical quantity are we representing with a certain distance on the diagram. So to take the example of a map, right? I'm not literally going to make a map of the United States and have it be the same size as the United States, right? I'm going to scale it down, right? So maybe a couple millimeters on the map might represent hundreds of miles, depending on the map, right? So that's the basic idea. But another example would be like a velocity vector, right? Velocities are measured in meters per second. Those aren't even physical lengths, right? So if I'm going to draw a velocity vector with a certain length, I'm going to have to specify, how much length corresponds to, I don't know, 1 meter per second or 10 meters per second, right? So one just example of how we could do this is like, let's say I have this graph paper with centimeter line markings all across it. Maybe each centimeter represents 1 meter per second of velocity. Okay, that's one possible scale factor we could choose, but really it could be anything you want, depending on the situation. But do we understand the idea? Okay, so we have a scale factor picked out. So the next thing we do is we take out a protractor, and we use that to measure the direction. So I literally just take a protractor, put it right here, and measure out however many degrees is specified as my direction, right? That means I know which way the vector is pointing. And then the next thing I do is I use a ruler to measure how long I should draw the vector. Because given my scale factor, I know how long my vector is supposed to be. Okay? Like how many centimeters I'm supposed to draw. So does that make sense? That's just how we draw one vector on a diagram. That's what we've established so far. So now that we know how to draw one vector, now we can talk about how to add multiple vectors together. Okay, we're going to learn about something called the tip-to-tail method. Has anyone seen the tip-to-tail method before? Sometimes called the head-to-tail method. Okay, let's talk about it. We'll learn about it. Okay, so let's start with the simplest case, which is we're just adding two vectors together. And then we'll talk about how to add any number of vectors. So let's say I just want to add two vectors together. Let's say the vectors are A and B shown here. The sum of those two vectors is what we typically call the resultant vector. So the thing that we get after we add A and B is called our resultant vector. Okay? So I'm going to call R A plus B. Okay, so this is how the tip-to-tail method works. First, we draw the vectors tip to tail. That means the end of one vector is connected to the start of another vector. So I would draw vector A, let's say, and then I would put the start of vector B at the end of vector A like this. That's them connected tip to tail. Okay? And once I've done that, I can then draw the resultant vector. The resultant vector just goes from the start of the very first vector I drew, which is over here, and then it ends at the end of the very last vector that I drew. So you chain them all together tip to tail, and then you draw a vector going from the very start of that chain of vectors to the very end of that chain of vectors. Okay? And remember, each one of these we know how to draw. We can measure it with a ruler and a protractor. Correct? So we put the two vectors on the diagram, we draw the resultant, and then guess what we do? For this resultant vector, I can measure straight off the diagram what is the magnitude. I can put a ruler up to the diagram and just say vector R is however many centimeters long. I can measure it directly. And I can also measure the direction because I can measure the angle using a protractor. Okay? So none of this involved calculation. It's all just drawing a diagram and making careful measurements. Okay? So any questions on how this works? Okay, the next thing I want to show you is just a more general picture of this approach. Okay, so in this picture, we just have two vectors connected together tip to tail. What if we had, I don't know, 4 vectors, 5 vectors, 3,000 vectors? It pretty much works the same exact way. Okay? You put them all in a chain, tip to tail, and you just keep going until you've included every single vector. Okay? So it really just depends on how many vectors you are trying to add together. You just need to do it twice if you have 2 vectors. You need to do it 100 times if you have 100 vectors. Whatever the case may be. Let's say in this case we have 4 vectors that we're trying to add together. We're trying to add A, B, C, and D. Those are the 4 vectors that we want to take the sum of. So the resultant vector R is A plus B plus C plus D. Okay, so again, this is just a random example. The exact way this looks depends on the situation. But let's say we have vector A pointing to the right like this. So we'll put that on the diagram to start. And then let's say we have vector B pointing into the first quadrant like this. It's connected tip to tail with vector A. See that? Then we have vector C, that's our next one. It's connected tip to tail. And then D, also connected tip to tail. So we've chained all 4 vectors together tip to tail. The resultant, it's the same as before. We go from the start of the first vector all the way to the end of the very last vector. So now that we have the drawing, the rest is the same as before. I can measure directly what the magnitude is just by how long the vector is, and I can measure the direction by taking an angle. Again, I'd probably use a protractor for that. Okay? So, are we good on how this works for 2 vectors or any number of vectors? Just as far as how we construct this picture? Okay, last thing to note about this is that the order doesn't matter. So in this particular picture, I drew A first, then I did B, then I did C, then I did D. Okay? I could have taken them in any order, and I would still get the same resultant vector. So it doesn't matter what order you choose to draw them in, you'll still get the same answer. It's important to remember. Order does not matter. Okay, so I think what we'll have time for is this example where we actually do this kind of careful measurement. Okay? So here's what we have. Vector A has a magnitude of 15 kilometers and a direction of 15 degrees off the x-axis. Okay? Vector B has a magnitude of 12 kilometers and a direction of 75 degrees. Vector R is the sum of A and B. So R is equal to A plus B. What we want to do is find that vector R, the resultant vector, after we add A and B, and we're going to do it using graphical methods, just by carefully constructing a diagram. We're actually going to come back to this problem on Thursday and do it using the algebraic methods, okay? And we'll see that we get the same answer, okay? So we're all clear on what's going on here? So let's get into this problem. Okay, so I remembered to bring a ruler and a protractor, okay? So I need this. Remember, the first step is I'm going to draw my x and my y axes, okay? So let's draw the x-axis. And just follow along with me. Your diagram is not going to be, as precise because you're not necessarily measuring it, but still draw it anyway because you want to get a sense of what this looks like, okay? So there's my x-axis. There's my y-axis. Okay. Okay, what is my first vector? It's let's just kind of do some side note work here. We say vector A has a magnitude of 15 kilometers, and the direction of this vector, which I'll call theta A, is 15 degrees. And that's off the x-axis. Okay, the second vector, that has a magnitude of 12 kilometers. And that makes an angle theta B, which is 75 degrees off the x-axis, okay? So I guess what I'll do is I'll start by drawing the first vector. I'll just have to measure it out, right? In terms of its length. So I'll just go ahead and draw a 15 kilometer long vector, right? No, of course not, right? I have to scale it down so it fits on the page. So what I'm going to do is choose a scale factor. Okay, so here's what I'm going to choose for my scale factor. I think this will work. Every 1 kilometer of physical distance is going to be represented by half of a centimeter of distance on my diagram. Does that make sense? So if I draw half a centimeter of distance on this page, it represents 1 kilometer. Okay? So actually, using that scale factor, let's real quickly, let's say what the magnitude of A should be. Because it's 15 kilometers in reality, but I'm going to scale it down according to this. And you can think of this like a conversion factor, right? Because every 1 kilometer is half a centimeter of distance on the diagram. So on the diagram, how long am I drawing this vector? So it's just 7.5 centimeters, right? Half of 15. Okay? How long am I going to draw vector B on my diagram? I have 12 kilometers of actual distance in reality, but I'm going to scale it down so that 0.5 centimeters on the diagram is 1 kilometer, and that gives us, what length should I draw on vector B? 6 centimeters, right? All right, so here's what I'm going to do. I'm going to take a vector, I'm going to measure it out to be 7.5 centimeters long, and then I'm going to make sure it's pointing at 15 degrees, and I'll draw a vector A to start. and then I'll draw vector B, and I'll make sure they're connected tip to tail. And then once we've done that, I can draw the resultant. Okay? So let's start by measuring out the angle. Okay? So I'm measuring my angle off the x-axis like this. And I want it to be 15 degrees. So that looks to be right about there. Does that look right? So that's the way my vector should be facing. But when I measure its length out, I want it to be 7.5 centimeters. So I'm going to take my ruler, start here at the origin, and then actually end right here, or like right here at 7.5 centimeters, okay? Okay, that's my first vector. Forget that part. I want it to stop here, right? And that's my vector A. That's our 15-degree angle. Okay, next I'm drawing vector B, and I want vector B to start right here where vector A ends. That's the way this works. So the first thing I'll do is measure out an angle. Now to make sure I'm measuring this out as well as I possibly can in the limited time we have, I'm going to draw a little dashed line like this, which represents the x direction, because I'm going to measure the angle off of this line as we go forward. Okay, so now in this case the angle is supposed to be 75 degrees, isn't it?
Yes.
Okay, so I'm going to measure out 75 degrees as best I can. This may not be perfect, but something like that, right? And then I'm going to make sure that this has a length. I'm going to kind of tilt this to measure the length so you can see it. I want to make sure this has a length of 6 centimeters. So looks like I want to start here and end here at 6 centimeters. That's good enough, let's say. Okay? So there's vector B, and there's our 75-degree angle. Okay, so that's A and B connected tip to tail. All good? So now our resultant vector is this one right here, because it starts where we started the first vector, and it ends where the last vector ends. So it's going to go like this. So this is our resultant vector, A plus B. Okay? What's the magnitude of that resultant vector? Let's just measure it. Okay, we can measure it directly. So I don't know about you, but I'm seeing just over just around 12, right? I think it's almost 12 on the dot. So let's just say 12.0 centimeters. That's on the diagram, remember. So what do? We want to convert it back to physical distance using the scale factor. So that means we're going to do 1 kilometer. We have a conversion factor where 1 kilometer is on top and 0.5 centimeters is on the bottom. So we have 12 over 0.5, which is 24. So we're getting, based off the diagram, 24 kilometers is the resultant vector, okay? Or at least that's the magnitude, right? For the direction, let's call that theta r. We'll measure that directly too. So we'll put up our protractor, and I don't know, what do you see for the direction here?
43, 42?
Yeah, it looks to be right about 42. I don't know if the numbers are too small to see. Do you see it? 42? Okay. 42 degrees. So we did this purely graphically. We didn't really calculate anything with the exception of using the scale factor to go back and forth between physical units and distances on the diagram. And this is pretty accurate. It's not exactly right because I didn't draw it as perfectly as it possibly could be drawn. But we'll see when we do the calculation of this result that we get something really close. So actually, just make sure when you come back on Thursday, you just have these numbers written down so you remember what we got when we did it this way. Okay? That's it for today. I'll see you guys on Thursday. Or if you're in lab today, I'll see you in lab tonight.